you know the index of refraction of the bubble, right? It's air relative to water. So you can do a really nice job modeling what the scattering will be. So here's the size distribution of the bubbles that were at various depths in the ocean. This is where they looked at the contribution to backscattering by bubbles of various sizes. And what you find is that basically bubbles that are between about 50 and 100 microns have the largest contribution to backscattering in the surface waters. And if you look at the total, this is the void fraction, which is essentially the concentration of bubbles, you can estimate how much backscattering is being contributed by bubbles by the points on this line. And so what you find is that under very, very high void fractions or high bubble concentrations, you get a lot of backscattering compared to the backscattering of seawater. And they also did a comparison based upon, well, I don't want to talk about that. Talk about that with another time. But essentially, bubbles don't make a big difference in low concentrations. It's only in very extreme white cap situations. And so that occurs, the bubble fraction, those high concentrations occur at very high wind speeds. So under very high wind speeds, you get a lot of bubble injection, and you will get enhanced backscattering. And it's not a surprise because when you look, like say from an airplane, you can tell when you see whitecaps and bubbles in the ocean. But again, Ken, what do they say about the contribution of bubbles like overall in the globe? Is it the missing backscattering that we're looking for? Not really, no. But important to take into account when you're looking in remote sensing. And I just wanted to show, this is actually a model of the volume scattering function of bubbles. And so there's a nice link here that talks about how to calculate the volume scattering function. And it's got some oscillations due to interference and constructive and destructive interference through the bubble. So I think, let me see where I was going to go with this. I may quit here. Emmanuel's going to talk about me theory and next week, which is modeling the volume scattering function and the scattering and the absorption of individual particles and populations of particles. And so we'll be looking at these types of characteristics in order to do that modeling. I'm just kind of forgetting where I'm going from here. Hold on just a second if I need to do this. Oh, yes, I do. Okay. Sorry. I just want to end with this. So you can take a particle of a certain size and you can model its index of refraction. So this is a 5 micron particle of various indices of refraction. And for an individual, for a suite of, or an individual particle, you can model its volume scattering function. And what you see, of course, is that the scattering is higher when the index of refraction is higher, right? When the index of refraction is lower, the scattering is lower, right? We already knew that. So you can also choose an index of refraction and change the particle size and see that large particles scatter more than small particles on a per particle basis, okay? And they have very different volume scattering functions. But then, if you think about the fact that we have suites of particles in the ocean, not just a 5 micron particle, you can think about adding up the effects, adding up the volume scattering functions for the whole distribution of your particles in the ocean. And so, some situations you might have a lot more small particles relative to large particles. Other situations in the ocean, you might have more large particles relative to small particles. And so the slope of this relationship between particle concentration and particle diameter will tell you something about what's in the water, but that will also impact the scattering that you might model. And so here is an example of some work that we did doing just that. So we were looking at particles of very steep or particles that were where you have more large particles relative to small particles, and you can see that the diffraction pattern is much different for each of these populations. And again, if you do the index of refraction, it doesn't make a big difference in the in the diffraction area. This is different particles of different index of refraction. And so I actually want to get to this point here. So I want to think about scattering closure and how you might measure scattering in a bulk sense in the ocean versus modeling it based upon the properties of particles that you can measure. And so the approach that Daria Stramsky and Kurt Mobley took in '97 was they measured the optical properties of a ton of different kinds of particles, of viruses, of protists, of phytoplankton of different sizes and pigmentation, of mineral particles. They measured the size distribution, the indices of refraction, real and imaginary, and they could predict both the absorption and the scattering and the volume scattering function of all these individual particles. Then you can begin to reconstruct what say a scattering coefficient might look like. If you know how many viruses you have, you know how many phytoplankton you have, you know how many protists that you have, how many air bubbles you might have in the water. Because IOPs are additive, you should be able to add all of those up. And so that's the approach that they took, and they predicted what a total volume scattering function might look like by adding up all those different parts. And so they compared it to what was an average volume scattering function that was measured a long time ago, and Kurt will talk about this volume scattering function. But you can see that you can do a pretty good job getting the overall shape of that curve, except in the backscattering area. And we're going to probably talk about this fact that we're not able to reconstruct the backscattering. And you can also model what the spectrum of scattering might look like. And here's the spectrum of scattering, and it's got some slope to it. And so if we think about closure, and if we actually could measure this spectrum, and we could measure the various concentration of all the materials in the water, we should be able to attain closure through these models. And so Darius has talked a lot about using this reductionist view and trying to get things to merge. And so it's something that we'll continue to talk about here as we begin to get pretty facile with being able to measure all of these different properties. So I think I will stop there. And I just want to end with this pretty picture. This is the radiance, the light field coming out of the Mediterranean Sea in two different wavelengths. So the ocean is very bright at 412, and it's not as bright at 490. This is normalized radiance. And so when you look at the patterns here, you should be thinking about what is causing that upward light coming out of the ocean at different wavelengths. And think about it in terms of absorption, which we talked about yesterday, and think about it with regards to scattering. So, as you compare sort of this end of the Mediterranean Sea and that end of the Mediterranean Sea with these two wavelengths, I want you to think about what processes might be happening in the water that would lead to these different patterns. Okay? Because that's ultimately where we're going, is what is the light that's coming out. Okay? Excellent. Questions? No? Okay.
I have a tiny question regarding this. When the date sort of...
Can you be back, please? You're asking a question.
She's asking a question, but it can be a small question.
Yeah, when the wave catches a particle, does it change
The wavelength.
direction? Yeah.
Oh, so what I on purpose drew this heading perpendicular, so the angle here is 90 degrees, so there's no refraction of this particular wave. It would shorten, so I should have actually drawn it shorter, right?
Would it change the phase as well?
Absorption doesn't change the phase. So the real part of the refractive index, that's what shortens up the wavelength. But the imaginary that is what absorbs. but there's no change in phase. There's no it doesn't shorten up. So if we had, say in this situation, that the real index of refraction relative to the medium, that it was the same, okay? So there's no difference between the index of refraction between the medium and the particle, but that n prime there was absorption. So we would have no shortening up. You would just have attenuation, right? Yeah. So the wavelength, the peak that it came out would be the same as if it hadn't gone through the particle. They would be lined up.
Okay.
Yeah.
Just wondered why the wavelength doesn't continue further down then.
Probably because I drew it incorrectly. I'm sorry. Yeah. No, that's a very good point. There. Is that better? Okay.
Thank you.
Yes. And of course, the particle is huge relative to the light. So, it's not hitting it at this angle. If we were actually looking at it on the correct scale, that would be the particle, and the light would be like this, right? But you're not seeing it. Yeah.
Thank you.
Yes. Good question. That's okay. That's okay. That's okay.